Welcome and hello. This is a video exercise in HEC HMS. And in this exercise, we're going to be dealing with the Clark unit hydrograph. In this exercise, we will be estimating the time of concentration and storage coefficient parameters for the Clark unit hydrograph transform method. All right, well, what I have on the screen is my HMS, so I need to go grab the project files first. If you click on the link in the description, it'll take you to this page right here, estimating Clark unit hydrograph parameters. And then once we make that estimation, we're going to do a little sensitivity analysis and take a look at the peak discharge and time to peak discharge. All right, what we have here are three links. The first is the introduction, and then at the end of that page, it links down to the next link here, estimating time of concentration and storage coefficient. And then finally, we'll be doing that sensitivity analysis on this third link here. So let's go ahead and just click the first link here and scroll through. What this is an overview. It provides the background and a little bit of information about what the next two pages have in store for us in this exercise. At the bottom of the page, there's a link to continue to the next page, so go ahead and click that. This is the page where we actually download the files, the starting files, and then start with the instructions. So scroll down just a little bit here, and then click this tc_r_initial.zip file, and then click the download button to begin the download. Okay, so that's downloading for me. It's on my desktop, and it looks like it's done here. So I'm just going to click the X to close that. Over here, I'm going to open up that zip file, and then open up this file here. All right, so this looks like my project, and it's called punks again. Punks.hms is the project file. So I'm going to go up one level in the Explorer window, and then I'm going to go ahead and just drag that over to a folder on my computer where I want to keep it permanently. All right, so now that that's copied over, it's unzipped, I can delete the original zip file and then open up the punks.hms file. So here's HMS, open, and then click Browse to navigate. Here is the project. So I open that up, and then punks.hms, and then click Select. All right, so the project files are loaded in my program. I'm going to expand the basin models directory and then click on this September 2018 map here, and then just bring it to screen. So there's way too many layers loaded for my preference. I'm just going to go View, Map Layers, and then just turn off some of these layers. Okay, so that's fine. What we have on the screen is good enough. We have three subbasins, a junction, a reach, and a sink. We're told to extract basin characteristics. That's for these three subbasins before we can perform the calculations. So what we need to do is go up to select the basin first, which we've done, and then go up to the parameters menu, and then click on characteristics and then subbasin. After we click that, it'll run the calculations to determine the parameters for our three subbasins. In this exercise, the time of concentration and the storage coefficient are our two primary parameters that we're interested in. For the Maud-Clark unit hydrograph, this is the equation that the instructions provide us for the time of concentration for this particular watershed. And it's right here, P sub C equals all of this. And then further down, the storage coefficient is R, and that equals 13/7 of the time of concentration. So both storage coefficient and time of concentration are in units of time, most commonly in hours. And these parameters here, L sub C, and the slope that we need to calculate the time of concentration are in this table here. I don't know if you can see that. I blew up the picture, but this longest flow path length in miles is the L variable. And then the third column over, the centroidal flow path length in miles is the L sub C variable. And then the sixth, 1, 2, 3, 4, 5, 6, this right here, the 1085 flow path slope, that's that third variable that's located in the denominator right here, slope 1085. I also want to point out that the instructions tell us that this slope 1085 is in units of feet per mile, and the values that were provided in this table are in feet per feet. So we have to multiply by 5280. Using the equations provided for time of concentration and storage coefficient, and of course the parameter values in this table here, I went ahead and opened up a Microsoft Excel file and performed those calculations. So what you're seeing here in each row, there's three rows because there's three subbasins and one subbasin per row. In the yellow cells here, these are the input values, which is the length, centroidal flow path length, and then the flow path slope. In yellow is the data I inputted. So we're seeing these three values here came from these three fields here, for instance. And then blue cells are calculated. So here I just multiplied by 5280. And then the time of concentration is a function of those three fields. And then the storage coefficient is just 13/7 of the time of concentration. And that's how I calculated the time of concentration and storage coefficients for my three subbasins. Step 3 of the instructions tells me to enter the time of concentration and storage coefficient into my subbasins manually. So I'll go ahead and do that. I'm going to go ahead and click on this subbasin here. This is the Mahoney Creek subbasin. And then what I have is the Clark unit hydrograph transform method already selected. That's good. So I'll click on transform tab. And then for time of concentration, I'll just type in my 7.02. And then the storage coefficient is 13.03. Okay, the Stump Creek subbasin, I'll type in that value. That's 5.86. The storage coefficient is 10.88. Save. And then the East Branch Mahoney Creek subbasin has values of 4.72 and 8.77. And save. Before running the simulation, the instructions at the very end of this page say that there's a way to automatically calculate these parameter values using the expression calculator in the global editor. So what I could do here is just go to parameters, transform method, Clark unit hydrograph, and I already have one selected. So let me clear the filter out. So what we're seeing here is a single view of the data we just typed in, but an easier way to get the exact same values is to just use this calculator tool. So I'm just going to go ahead and demonstrate that real quickly. So I've cleared out all the data that I just added in, and now I'm going to click on this calculator here. What I do is for field, I'll select time of concentration, and then after that, I'll calculate the storage coefficient. The time of concentration right here will be based on these statistics. Now, these rows are basically the same values that we saw in that table, which were separated by individual columns. The instructions provide us the equation to use right here. So this is the 2.2 times, and then there's that quotient all raised to the 0.3. So I think all I have to do now is click calculate, and then it's running. And then these are the three values that I just typed in previously. If I wanted to calculate the storage coefficient, I can just use the exact same equation, but then at the beginning, type in something like 13 divided by 7. And then let's go ahead and click calculate there. And now those numbers are populated. So I'll go ahead and close that. Then I'll click apply. Then I'll click close. When we downloaded this project, the simulation that we want to run has already been created for us. So we don't have to create the control specification or the MET model or anything like that. But I did want to peek at the control specification. This is from the beginning of September 2018 all the way for the next 4 weeks through the 28th at a 1-hour time step. So I'm just going to leave that as it is. Go ahead and click save and then run the simulation. Now that the simulation has completed, let's take a look at some of the results. So I'll click on the Results tab here in the Watershed Explorer, expand the simulation run results, and now we have our different results we can choose. For instance, the global summary here shows our drainage area, peak discharge, time to peak discharge, and volume for our different hydrologic elements. We're most interested in the Mahoney Creek at Punk's Gauge element, which is the sink at the bottom of our network. All right, so I'm going to go ahead and close that. Also, we can click on the individual hydrologic elements and then click on the graphs and the summary tables and so on. So if I click on the graph for this bottom element here, we see the different hydrographs, and we can compare that observed flow versus the actual computed flow. If I zoom in on the peak flows very briefly, we have the observed flow in black and then the computed flow in solid blue line here. If you're following along in the tutorial, then that's the end of step 5 here. And then this bonus step 6 is about using that calculator that we already did. And then the final files if you want, a couple questions. And then at the end, it invites you to click this link to go on to the next part of our exercise. So go ahead and do that. Now what we're going to do is change the time of concentration and storage coefficient values for the same basin model that we had for all three subbasins and figure out how those changes affect the peak discharge and the time to peak discharge. So let me go ahead and get started with that. The instructions tell us to start by creating 4 new basin models. So we'll go to the Components tab in the Watershed Explorer. I'm going to click on the one basin model that we have, September 2018, right-click on it, and then go Create Copy. So the first basin I'm going to create a copy of, I'm going to call it double TC. So September 28 dash double TC copy. Then I'm going to make another copy by right click, create copy. This one's going to be called half TC copy. Right click, create copy. Then it's going to be double R referring to the storage coefficient. And then the last copy we make is going to be called half R, referring to half the storage coefficient, and copy. Next, we're told in step 2 to create 4 new simulation runs. So I'll click on the Compute tab here. I'll expand. Here's our simulation run, and I'm going to right click, create copy. Now, the first copy we're going to make is going to be called double TC. So it's just basically going to be have the same names as we named our new basins. Okay, let's make a second copy here. So our third total simulation run, this will be half TC. The next copy will be called double R for double the storage coefficient. And then the last copy of the simulation run will be half R for half the storage coefficient. Next, what we need to do is actually change the basin model that is assigned to each of these simulation runs. So the original here is fine. We're going to leave that there. But for double R, double storage coefficient, I need to come down here to the basin model and select September 2018 double R. All right. And then for double TC, I'll just do the same thing, but double TC, half R, basin model, half R, and then half time of concentration. The basin model will be half a time of concentration. Save. Now we actually have to change the values themselves by either doubling or halving the time of concentration and storage coefficient. So I'll click on the Components tab in the Watershed Explorer, and let's just go from top to bottom. So the basin here is double storage coefficient. I think the quickest way to do this would be from the global editor. I'll click on Parameters, Transform, Clark Unit Hydrograph, and I said double storage coefficient. So these values here, paste, are all going to get doubled, and then I'll click Apply, and then Close. All right, let's move on to the next basin. That's going to be double time of concentration. So I'll click on Parameters, Transform, Clark Unit Hydrograph, and then I'll select the time of concentration values and then paste in the double of that value, Apply, Close. Then I'll collapse that basin model. Next is half R, half the storage coefficient. Parameters, Transform, Clark Unit Hydrograph. So instead of the original values, there'll be half of the original values, and then Apply, and then Close. And then let me just collapse that. The last one is half of the time of concentration. Parameters, Transform, Clark Unit Hydrograph, and then I'll go ahead and paste in the half time of concentration. Apply, Close, and Save. All right, next what we need to do is run the simulations, all 4 of them. So I'm just going to come over to here to the Compute tab. We've already computed the original. I'll just call this like the normal or the base simulation. So let's go ahead and compute these 4, starting with double R from top to bottom. Right click, compute. Just wait a moment. The next one down is double time of concentration, compute. Next one is half R. So I'll go ahead and compute that one. And the last one is half of the time of concentration. Next, it's time to take a look at those results and see what effect changing that time of concentration and storage coefficient had on the peak discharge and time to peak discharge. So one way to do that is to go to the Results tab. And then what I'm going to look at first is the time of concentration. So to do that, I'm going to expand the basins with different times of concentration, which will, of course, be our original. And then it will also have our double time of concentration and half time of concentration. And then what I want to look at is the sink, which is this element here, the computation point element, Mahoney Creek at Punk's gauge. So I'm going to expand that for the same 3 basins that I already expanded. Okay, cool. So now what I want to do is look at the outflow right here. So what I'm going to do is click on it with a single left click for the half time of concentration. I'm going to scroll up and click on the outflow for the double time of concentration. And now the original or the normal time of concentration right here. So I got 3 different time series loaded up into this plot. Now this is just a little preview graph. You can't see it too well down here, but if we click the graph button up here in the compute toolbar, It opens up in its own window and allows us to view it a little easier and allows us to zoom in. Okay, so I'm going to zoom in here on the peaks. So what we have here is in solid blue, this is the half time of concentration. And then the next series over, this one right here, this is the original time of concentration. And then right here is double time of concentration. So I think we can conclude that as the time of concentration increases, the time to peak discharge also increases. I think that's pretty straightforward, no surprises there. But then the peak discharge we notice actually is maximized at this normal time of concentration. Also, looking at the scale, the actual peak discharge doesn't really change too much. So what we can do is look at the actual numbers from these results as well. If I look at the actual results in the summary table, we can see what those numbers look like. 7,211 CFS is the peak discharge for our normal time of concentration, and that's at September 10th at 11 p.m. So keep that number in mind. And then if we look at the double time of concentration and then click on the summary table, we see it's 7,006 CFS, and it's a few hours later at 2 a.m. And then the last one, the summary table, this is half the time of concentration, the 7,148 CFS, and that's a couple hours earlier for the peak discharge. All right, let's do the same thing with the storage coefficient. I'm going to go back up to the top, and then I'm going to collapse the results pertaining to the time of concentration. And then I'm going to expand the results pertaining to the storage coefficients, where we're doubling and halving those. And then again, expanding the Mahoney Creek at Punk's gauge right there and there. So what I'm going to do is click on the outflow plot. This is for half storage coefficient. And then again, for double storage coefficient, I'm holding down control. And then with control still held down, here's the normal storage coefficient value for R. So those three time series are loaded up in my preview. I'm going to click the plot right here. And then let's zoom in on this a little bit. So what we have here in solid blue is the peak discharge. This is the time series hydrograph for the half storage coefficient. And then let's see, the next one here is the normal storage coefficient, the original value. And then the last one here at the bottom is the double storage coefficient. Judging by the values here in the vertical axis, the flow rate, there's a huge variation in the peak flow rate based on that storage coefficient. However, just like the time of concentration, there doesn't seem to be a huge difference in the time to peak discharge, maybe just a few hours. As with the time of concentration, I can also look at the summary tables for each one like this, but instead of opening them up, I'm going to just bring up my results table. So here's the results table I was talking about. What I did in the first part of the simulation was I changed the time of concentration and held the storage coefficient the same. And then in the next couple trials, I had held the time of concentration constant and then changed the storage coefficient. So this line right here for normal is the same data as this line right here. I just copied it over because I thought that that would be a little bit more appropriate and easy to visualize, at least looking at the numbers, what's happening here. My number one takeaway from this table and this exercise altogether is that the peak discharge is more sensitive in changes to the storage coefficient than to changes in the time of concentration. So as we're changing the time of concentration here, there's not a huge change in the peak discharge. But as we change the storage coefficient, we're seeing a large change in that peak discharge. I don't really have any conclusions to draw about the time to peak discharge because those numbers are not particularly different between the two different runs. Well, that's it for this exercise on the Clark unit hydrograph. We used equations to initialize our time of concentration and storage coefficient, which are the different parameters that are used for this particular transform method. And then we also did some sensitivity analysis to see what effect those parameters had on the peak discharge and the time to peak discharge.